4.2 light-years away, there's a star. Not just any star. Our closest neighbor beyond the Sun, Proxima Centauri. For decades, we've stared at it, wondering, are there worlds there? Could they harbor life? In 2016, we found a planet, Proxima b, Earth-sized, in the habitable zone, the dream scenario. Then James Webb looked at it, and what it saw wasn't in any of the textbooks. Welcome back to Beyond Space. Where we explore the universe one mind-blowing idea at a time. If you're new here, hit that subscribe button, because today we're diving into one of the most fascinating and frustrating mysteries in modern astronomy. The James Webb Space Telescope was built to see the impossible, to peer through cosmic dust, to catch the faintest whispers of light from the universe's infancy, to study the atmospheres of distant worlds with unprecedented precision. And naturally, scientists wanted to point it at the one place that matters most to us, our cosmic backyard. Proxima Centauri, a small, dim red dwarf star just 4.2 light-years away. Close enough that if we ever hope to send probes to another star system in the next century, this is it. Orbiting this star is Proxima b, discovered in 2016, an Earth-mass planet in the habitable zone, where liquid water could theoretically exist. On paper, it's the Holy Grail, a potentially habitable world practically next door. But there's a problem, actually, several problems, and James Webb was about to expose every single one of them. This is the story of what happens when the most powerful telescope ever built turns its gaze toward our nearest neighbor, and the universe refuses to give us easy answers. Act 1. The Promise of Proxima. Let's set the stage. Why does Proxima Centauri matter so much? Proxima Centauri is what's called an M-dwarf, or red dwarf star. It's tiny, about 1/8 the mass of our Sun, and only about 1.5 times the diameter of Jupiter. It's so dim that despite being our closest stellar neighbor, you can't even see it with the naked eye. But proximity changes everything. At 4.2 light-years, Proxima Centauri is close enough that our fastest current spacecraft would take tens of thousands of years to reach it. But future technologies, light sails, fusion drives, could potentially cut that down to decades. If humanity ever sends a probe to another star, this is the target. In August 2016, astronomers announced something extraordinary. They'd found a planet around Proxima Centauri using the radial velocity method, detecting the tiny wobble the planet's gravity causes in its star. Proxima b, minimum mass, 1.17 times Earth. Orbital period, 11.2 days. Distance from its star, just 0.05 astronomical units, closer than Mercury is to our Sun. But here's the kicker. Because Proxima Centauri is so dim and cool, that orbit places Proxima b right in the middle of the habitable zone, the Goldilocks region where temperatures could allow liquid water. The media went wild. Headlines screamed about Earth's twin next door and the closest potentially habitable world. Science fiction suddenly felt within reach. But astronomers knew something the headlines didn't emphasize. Red dwarf stars are violent. Unlike our relatively calm Sun, red dwarfs are prone to massive stellar flares, eruptions of radiation and charged particles that can strip away planetary atmospheres. Proxima Centauri is particularly active, unleashing flares that increase its brightness by factors of 10 or more. For a planet orbiting so close, tidally locked with one face always toward the star, the radiation environment would be brutal. Any atmosphere would be under constant assault. Still, hope remained. Maybe the planet had a strong magnetic field. Maybe it formed with enough water that even after losing some atmosphere, oceans could persist. Maybe, just maybe, we could detect biosignatures. And that's where James Webb came in. Act 2. JWST takes aim. When JWST's commissioning phase ended in 2022, Proxima Centauri was on the target list. The plan was ambitious but straightforward. Use Webb's infrared instruments, particularly NIRS, PEC, and MIRI, to observe Proxima b during transit, if possible, or through direct thermal emission. Look for molecular signatures: water vapor, carbon dioxide, methane, oxygen, the fingerprints of an atmosphere. If Proxima b had a thick atmosphere, JWST should be able to detect it. This was the telescope's bread and butter. It had already stunned the world with atmospheric detections of hot Jupiters and mini-Neptunes thousands of light years away. Proxima Centauri was right here, just 4.2 light years. If JWST could characterize atmospheres across the galaxy, surely it could nail this one. Except, there was a problem, a big one. We don't know if Proxima b transits. The radial velocity method that discovered it tells us the planet exists and gives us a minimum mass, but it doesn't tell us the orbital inclination. If the orbit isn't aligned just right from our perspective, the planet never passes in front of its star from our point of view. Statistically, the odds of a transit for a planet this close to its star are only about 1.5%. Early observations found no transits. That meant transmission spectroscopy, the easiest method, was off the table. So scientists pivoted. Plan B: detect the planet's thermal emission directly. Measure the combined light of the star and planet, then subtract the star's light, leaving only the planet's heat signature. It's incredibly difficult, like trying to spot a firefly next to a searchlight from across a football field. But JWST was built for this. Between 2022 and 2024, multiple teams secured time on JWST to observe Proxima Centauri. They used NIR SPEC and MIRI to capture spectra across multiple wavelengths, looking for any deviation that could indicate a planetary atmosphere. Hours of integration time, careful calibration. The data started coming in, and that's when things got weird. Acti 3: The unexpected signals. The first hint of trouble came from the star itself. Proxima Centauri isn't just flare-prone, it's magnetically complex. Its surface is covered in star spots, like sunspots, but more extreme. And its chromosphere, the layer above the visible surface, is active and variable. When JWST looked at Proxima Centauri, it saw signals, spectral features that could be interpreted as molecular absorption, water, carbon dioxide. Exactly what you'd hope to see from a planet with an atmosphere. But here's the problem: those same features can be produced by the star itself. Red dwarf stars have thick, extended chromospheres. Unlike the Sun, where the chromosphere is a thin layer, M-dwarfs have chromospheres that can dominate their spectra, especially in the infrared where JWST operates. Molecules like water vapor, carbon monoxide, even complex hydrocarbons can exist in the star's outer atmosphere. When you're trying to detect a planet's atmosphere, which contributes maybe 0.01% of the total light stellar contamination, becomes a nightmare. Teams ran models. They tried to subtract the stellar contribution. They compared observations taken at different times when the planet was on opposite sides of its orbit, hoping to isolate the planetary signal. And in most cases, the signal vanished. What looked like a planetary atmosphere in the raw data turned out to be stellar noise. Then there were the flares. During some JWST observations, Proxima Centauri flared, sometimes dramatically. These events inject huge amounts of energy across the spectrum, overwhelming any subtle planetary signal. One team's observation was essentially ruined by a flare event. Months of planning, precious telescope time, compromised by the star's unpredictability. So what did JWST actually find? As of 2024, the consensus is frustrating but scientifically honest. JWST has not definitively detected an atmosphere around Proxima b. The data is consistent with either a thin atmosphere, heavily contaminated by stellar signals, or no atmosphere at all. Some models suggest that if Proxima b ever had a thick atmosphere, it's likely been stripped away by stellar radiation over billions of years. The planet could be a barren, irradiated rock, more like a hot Mercury than an Earth. But, and this is crucial, the data doesn't rule out an atmosphere entirely. It just means we can't confirm one yet with current techniques. Act 4. What this means for the search. Proxima Centauri taught us something vital. Proximity doesn't equal simplicity. Red dwarf stars make up about 75% of all stars in the galaxy. They're the most common stellar type, and statistically, they host the most planets. If we want to find habitable worlds, we can't ignore them. Systems like TRAPPIST-1, 7 Earth-sized planets around an ultra-cool dwarf, are high-priority JWST targets. But Proxima Centauri showed us that stellar activity is a massive obstacle. Every red dwarf is a chaotic flare-spitting furnace, and disentangling planetary signals from stellar noise is extraordinarily difficult. The good news, we're learning. New data analysis techniques are being developed specifically to handle stellar contamination. Future missions, like the Habitable Worlds Observatory or next-generation ground-based telescopes with advanced adaptive optics, will be designed with these challenges in mind. And there's another approach, direct imaging, actually photographing the planet as a separate point of light from its star. For a system as close as Proxima Centauri, this might be possible with next-generation coronagraphs and starshades. There's even Breakthrough Starshot, a proposal to send tiny, light sail-propelled probes to Alpha Centauri at 20% the speed of light. They'd arrive in about 20 years and send back actual images of Proxima b. Imagine that. Not spectroscopic data, not models, actual photographs of the closest exoplanet to Earth. But here's what Proxima Centauri really taught us. The universe doesn't owe us easy answers. We built the most powerful telescope in history. We pointed it at our nearest neighbor, and the cosmos said, "Not yet, you need to work harder." And that's okay, that's science. Every challenge reveals a deeper layer of complexity. Every failure refines our methods. Every unexpected result teaches us something new about how stars and planets actually work, not how we wish they worked. So here's my question for you. Do you think Proxima b has an atmosphere? Or has it been stripped away by billions of years of stellar bombardment? Drop your thoughts in the comments. I want to hear what you think. And here's a bonus question. If you could send a message to Proxima Centauri, knowing it would take over 4 years to get there and another 4 for a response, what would you say? Let me know below. Proxima Centauri is still there, 4.2 light-years away, waiting. We may not have all the answers yet. James Webb may not have given us the clear-cut detection we hoped for. But every observation, every data point, every challenge overcome brings us closer to understanding our place in this vast, mysterious universe. The search isn't over, it's just beginning. And the next breakthrough could come tomorrow or next year, or from a telescope that hasn't even been built yet. But one thing is certain, we're not giving up. Because somewhere out there, orbiting a small red star in the darkness, there might be a world. And we're going to find out. Thanks for watching. If you enjoyed this deep dive into one of astronomy's most fascinating mysteries, hit that like button and subscribe for more cosmic explorations. Until next time, keep looking up.